Welcome to the Deep Dive. Today we're really getting into something fundamental for understanding networks, connections, basically graph theory.
Yeah, and not just, the bar chart kind of graphs. We mean the ones with dots and lines, vertices, and edges that model relationships.
Exactly. Everything from social networks to, I don't know, supply chains. And we're zeroing in on two really core ideas today: Eulerian and Hamiltonian graphs.
Right. Think of this as like a focused study session. We're going deep into the definitions, the theorems, the applications.
We've got some great source material covering all that, definitions, theorems, even touching on directed graphs later.
Yeah.
And algorithms too.
The goal really is to break it down thoroughly, almost like we're prepping for an exam on this. We want everyone listening to get why these things work, not just what they are.
Okay, perfect. Let's jump right in then. Eulerian graphs and walks. First up, what exactly is an Euler line? Let's nail that down.
Okay, so an Euler line is a closed walk, meaning it starts and ends at the same spot, and it manages to hit every single edge in the graph exactly one time. No repeats on the edges.
And a graph that has one of these lines, that's an Euler graph.
Precisely. And a really important point right away, an Euler graph has to be connected.
Yeah, that makes sense, right? If you've got bits floating off disconnected, how could one single walk possibly cover all the edges?
Exactly, you just can't get there. And that leads us straight into, well, a really foundational theorem, Theorem 2.1.
Ah, yes. The big one for Euler graphs. It gives us the condition, right? The if and only if.
That's the one. It states, a connected graph is an Euler graph if and only if all of its vertices have an even degree.
Even degree, meaning an even number of edges touching each vertex.
Okay, that's a powerful statement. Let's maybe unpack the proof a bit. It helps solidify it, I think.
Definitely. Good idea for our test prep. Let's take the if part first. So if a graph has an Euler line, then all its vertices must have an even degree.
Okay, why? Let's imagine tracing that line.
Right. Think about any vertex that's not the start or end point. Every time your walk enters that vertex using one edge.
It has to leave using a different edge because you can't repeat edges.
Mm-hmm.
Exactly. So one edge in, one edge out. That's two edges used for that vertex each time you pass through it. So it contributes 2 to the degree count for each pass.
Okay, that covers the intermediate vertices. What about the start end vertex? It's the same point since the walk is closed.
Good question. Well, you start by leaving it, that's one edge. You end by arriving back at it, that's another edge. And if the walk happens to pass through it in the middle?
It uses one edge in and one edge out again, so 2 more.
Right. So every time that start end vertex is involved, it's always in pairs of edges, one out, one in. Since the Euler line uses every single edge exactly once, every vertex ends up having its total degree count incremented in pairs. Therefore, every vertex must have an even degree.
Okay, tracing it like that makes it click. That direction feels pretty solid. Now, the other way around. The only if part.
The sufficiency part, yeah. If all vertices in a connected graph have even degree, then it must contain an Euler line. This part's a bit more involved. It's a constructive proof.
Meaning we have to show how to build the line.
Exactly. So you start at any vertex you like, call it V, and you just start walking. Follow any edge, then another. The only rule is don't reuse an edge you've already walked.
Okay.
Now, here's the key. Because every vertex has an even degree, whenever you enter a vertex, that is an eve right at the end, you know there must be an unused edge leaving it.
Why? Because if you use one edge to get in and the total degree is even, there has to be at least one more edge left to get out. Unless you're back at the start.
Precisely. You can never get stuck at an intermediate vertex. You always have an escape route, an unused edge to leave on.
So you keep walking, never repeating edges until when? When do you stop?
You stop when you can't move anymore without repeating an edge. And the proof shows that the only place this can happen is back at your starting vertex.
Because any other vertex would have meant you entered it one last time, and since its degree was even, there had to be an exit edge unless all edges connected to it were already used. But if they were all used, you must have both entered and exited an even number of times.
Oh, I see. So you can only get stuck back at V. You got it. You trace out a closed walk, let's call it H, but maybe this walk H didn't use up all the edges in the original graph G.
Right. That's possible. What then?
Okay, this is the clever bit. You mentally remove all the edges that you just used in your walk H. What you're left with is a subgraph. Let's call it G prime or something.
Okay, the leftover edges and their vertices.
Now, think about the degrees in this leftover graph. The original graph G had all even degrees. Your walk H also used edges in pairs at each vertex. So if you subtract the H edges from the G edges...
The remaining graph G prime must also have only vertices with even degree.
Exactly. And because the original graph G was connected, this leftover graph G prime must touch your first walk H at least at one vertex. Let's say they touch at vertex A.
Okay, so vertex A is on our first walk H and also has some leftover edges attached to it in G prime.
Right. So now, starting from A, you can trace another closed walk, this time using only edges from G prime. You can do this for the same reason as before. All vertices in G prime have even degrees.
Ah, so you find a second closed loop within the leftovers, starting and ending at A.
Yep. And then you just splice it in. When your original walk H reached vertex A, instead of continuing directly on H, you take a detour around this new closed walk from G prime, and when you get back to A, you then continue along the rest of H.
Creating a new, bigger closed walk that includes all the edges from H plus all the edges from the second walk.
Exactly, and you just keep doing this. If there are still leftover edges, they'll form another subgraph with even degrees connected to your current bigger walk. Find a closed loop in that, splice it in.
And you repeat until no edges are left. And you end up with one giant closed walk that covers every single edge. An Euler line.
That's the construction. It's quite elegant, really. It guarantees that if the condition, connected all even degrees, holds, the Euler line must exist.
It really is satisfying, and the perfect example to see this in action is the classic Königsberg Bridge problem.
Ah, yes. A historical gem. Can you set the scene?
Sure. So, old city, Königsberg. There's a river running through it with two islands in the middle, and there were 7 bridges connecting the islands to each other and to the two banks of the river.
Right. 4 distinct land masses in total. 2 banks, 2 islands.
And the puzzle everyone was apparently obsessed with was, could you take a walk, starting anywhere, cross each of those 7 bridges exactly once, and end up back where you started?
Okay, so how do we turn this map puzzle into a graph problem, to use our shiny new theorem?
Simple enough, actually. Each of the 4 land areas becomes a vertex.
Okay, 4 vertices.
And each of the 7 bridges becomes an edge connecting the vertices that represent the land areas it links.
Got it. So we have a graph. 4 vertices, 7 edges. Now, what's the crucial next step, thinking about Theorem 2.1?
We need to look at the degrees of the vertices. The degree of a vertex here is just the number of bridges connected to that land area.
Right. So let's count. If you look at the map, the North Bank had, I think, 3 bridges. The South Bank also had 3. One island had 5 bridges connected to it, and the other island had 3.
Wait, so the degrees are 3, 3, 5, and 3. None of those are even.
Exactly. And that's the aha moment, since not all vertices in the Königsberg Bridge graph have an even degree.
Theorem 2.1 tells us definitively it is not an Euler graph.
Which means?
It means the walk is impossible. You cannot cross each bridge exactly once and return to your starting point. Wow, that's neat.
Isn't it? A real-world puzzle solved cleanly by abstract mathematics. A cornerstone moment for graph theory.
Okay, so that's Euler lines, Euler graphs, the theorem, Königsberg.
Ooh.
What of these unicursal lines mentioned? Sounds similar.
Very similar. A unicursal line is basically an open Euler walk. It still traverses every edge exactly once, but it starts at one vertex and ends at a different one.
Ah, so not a closed loop. And a graph with one of these is a unicursal graph.
Correct. The examples usually show a path clearly starting somewhere and ending elsewhere, having hit all the edges.
Is there a connection between the closed Euler lines and these open unicursal lines?
A very direct one. Imagine you have a unicursal line going from vertex A to vertex B, hitting all edges once.
Okay.
Now, what if you just drew in a new edge directly connecting B back to A?
Then you'd close the walk. You would become an Euler line in that slightly modified graph.
Precisely. And that insight leads directly to the condition for a graph to be unicursal. It's related to the vertex degrees again.
Okay, if an Euler graph needs all even degrees, what does a unicursal graph need?
It needs to have exactly 2 vertices with odd degrees. All the other vertices must still have even degrees.
2 odd degrees. Why does that make sense?
Well, think about the open walk. The starting vertex has 1 edge left over when you count pairs, the first step out. The ending vertex has 1 edge left over, the final step in. All the intermediate vertices must have edges used in pairs, in and out.
Ah, so the 2 odd degree vertices have to be the start and end points of the unicursal line.
Exactly. A connected graph is unicursal if and only if it has precisely 2 vertices of odd degree.
Okay, what if a graph has, say, 4 odd degree vertices? Or 6? What then?
Now we're getting to Theorem 2.2. It generalizes this. If a connected graph has 2k odd vertices, so an even number of them, like 4, 6, 8.
Okay, K2 for 4 odd vertices, K equals 3 for 6.
Right. Theorem 2.2 says you can actually break down that entire graph into k separate edge disjoint subgraphs. And each of those subgraphs will itself be a unicursal graph.
Whoa. So if I have 4 odd vertices, I can find 2 separate open walks, unicursal lines, that together use up all the edges of the original graph without sharing any edges between them.
That's exactly what it guarantees.
How does that work? What's the idea behind the proof?
It's another clever construction. You start with your 2k odd vertices. You can arbitrarily pair them up, v1, w1, v2, w2, vk, wk.
The K2 source.
Then you imagine adding new edges to the graph, one edge connecting each pair. So add an edge between v1 and w1, another between v2 and w2, and so on.
What does adding those specific k edges do to the vertex degrees?
Well, you've just added one edge to each of the original 2k odd vertices, which means
Their degrees all just increase by 1, making them even, and the originally even vertices are untouched, so they stay even.
exactly. So this new augmented graph, original edges plus the new ones, now has all vertices with even degrees. And assuming it's still connected,
It must be an Euler graph by Theorem 2.1. It has a closed Euler line that uses all the edges, including the new ones.
right. Now picture that Euler line. What happens if you just erase the k artificial edges you added?
Well, each time the Euler line used one of those k fake edges, removing it would break the walk at that point.
Precisely. Since you remove k edges, you break the single closed Euler line into k separate open walks.
And those open walks use only the original edges. And because the Euler line covered everything, these k walks together cover all the original edges.
And each one starts and ends at one of the pairs of odd vertices you originally connected. So you've decomposed the graph into k-edge disjoint unicursal lines.
That's really cool. It shows how even graphs with many odd vertices still have this underlying Eulerian structure, just broken into pieces.
It's a powerful way to think about traversing networks. Okay, maybe we should shift gears slightly and talk about some basic ways we can combine or modify graphs. These operations are kind of like the building blocks.
Sounds good. Things like union, intersection, those basic set operations, but for graphs.
Exactly. Let's start with the union, G1 or G2. Pretty straightforward, right?
Yeah, you just take all the vertices from both graphs, put them together, take all the edges from both graphs, put them together. That's your new graph.
And importantly, order doesn't matter. G1 union G2 is the same as G2 union G1. Commutative.
Okay, then intersection, G1 or G2.
More restrictive. You only keep the vertices that are in both G1 and G2, and you only keep the edges that are in both G1 and G2.
So if they don't share any edges, the intersection is just vertices, or maybe nothing.
If they share no edges, the intersection graph has no edges. It's a null graph. It might have shared vertices, though. If they don't even share vertices, the intersection is completely empty. And again, commutative.
Got it. Then there's the ring sum, G1 or G2. That symbol looks a bit like XOR.
It basically is XOR for the edges. You take all the vertices from both, like the union. But for the edges, you take an edge if it's in G1 OR G2, but not if it's in both.
Ah, the exclusive OR. So if an edge exists in both graphs, it gets excluded from the ring sum.
Exactly. Also commutative. And an interesting property, if G1 and G2 have no edges in common, their edge disjoint, then their ring sum is actually the same as their union.
Okay. And what about G or G? A graph ring summed with itself.
That always gives you a null graph, no edges, because every edge is in both, so they all get excluded by the XOR condition.
Right. These operations lead into the idea of graph decomposition. Yeah.
They do. Decomposing a graph G means splitting it into two subgraphs, say G1 and G2, such that, well, two things have to be true.
Okay, what do I...
First, their union must give you back the original graph G, at least in terms of edges. All original edges must be in G1 or G2.
So G1A, G2 for edges.
Right. And second, their intersection must be empty in terms of edges. They can't share any edges. They must be edge disjoint.
G1UA, G2 edges is empty, but they can share vertices.
Oh, yeah, vertices can definitely be shared. And any vertices left isolated after you split the edges are usually just ignored. The material even gives a formula. If G has M edges, the number of ways to decompose it into two such edge disjoint subgraphs is 2M and 1, 1.
Huh. Interesting formula. Okay, what about operations that remove things? Like deleting a vertex.
Vertex deletion, GV. If you remove vertex...
You obviously remove the vertex itself, but you also have to remove all the edges that were connected to it, right?
Exactly. All incident edges go to. You're left with a sub-guy.
And edge deletion, GEJ.
Simpler. You just remove that specific edge, EJ. The vertices at its ends stay put. All other edges stay put.
It's just plucking out that one connection.
Right.
The material mentioned this is related to the ring sum.
Yeah, GEJ is actually equivalent to GEJ, where EJ here represents a tiny graph containing only that single edge and its two endpoints.
Neat trick. And the last operation mentioned was vertex fusion, merging vertices.
Right. You pick two vertices, say A and B. You squish them together into one new super vertex.
Okay. What happens to the edges?
Any edge that used to connect to A or used to connect to B now connects to this new fused vertex.
So the number of vertices goes down by 1, but the number of edges stays the same.
That's right. The connectivity just gets rerouted to the new merged vertex.
Got it. So union, intersection, ring sum, decomposition, deletion, fusion, a whole toolkit for messing with graphs.
Exactly. And understanding these helps analyze properties like the Eulerian ones we talked about or the Hamiltonian ones we're about to get into.
Right, Hamiltonian paths and circuits. So we switch focus now from edges to vertices.
Precisely. Eulerian was about traversing every edge once. Hamiltonian is about visiting every vertex exactly once.
Okay, so let's define a Hamiltonian circuit first. What's the deal?
A Hamiltonian circuit is a closed walk, starts and ends at the same vertex, but the key rule is it must visit every other vertex in the graph exactly one time along the way.
Every vertex, exactly once, back to the start. Like a salesman visiting every city on their list once and returning home.
That's the classic analogy, yes. The traveling salesman problem is very related.
And if you have a Hamiltonian circuit and you just snip one edge out of it?
Then you get a Hamiltonian path. It's an open walk, starts at one vertex, ends at another, and visits every single vertex in between exactly once.
So if a graph has n vertices, a Hamiltonian path would have n1 edges.
Exactly, n1 edges, yeah.
Now, because you have to visit each vertex exactly once, does that rule out certain kinds of edges, like self-loops or parallel edges?
Absolutely. You can't use a self-loop because that would mean visiting the same vertex twice in a row. And you wouldn't use parallel edges because you only need to get between two vertices once on the path or circuit. So we're usually talking about simple graphs here.
Okay, let's talk about complete graphs for a second. Remind me what those are.
A complete graph, K(n), is a simple graph where every single pair of distinct vertices is connected by exactly one edge. Maximum connectivity.
Like K5 is 5 vertices with edges connecting every pair.
Okay.
Are these easy to find Hamiltonian circuits in?
Oh yeah, very easy. In a complete graph, you know all the connections exist.
So you could just pick an order for the vertices, V1, V2, V3, up to Vn.
Yep, and just follow the path V1 to V2, V2 to V3, Vn1 to Vn, and then, because it's complete, you know there's an edge from V bend straight back to V1.
Boom. Hamiltonian circuit. Guaranteed. Because all the required edges exist.
Exactly. The completeness makes it trivial.
Now, Theorem 2.3 talks about finding multiple Hamiltonian circuits in complete graphs, ones that don't share edges. What's the condition?
Right, edge disjoint circuits. The theorem says in a complete graph K and N, if N is odd and N is 3 or more.
Okay, K3, K5, K7, etc.
Then you can find exactly N12 edge disjoint Hamiltonian circuits.
N12, let's unpack that. Why that number? How does the proof work?
Well, first, think about the maximum possible. A complete graph Kn has N(n)(1)(2) total edges.
Okay.
And any single Hamiltonian circuit uses exactly n edges. So the absolute maximum number of edge disjoint circuits you could possibly fit in is total edges per circuit, Nn12, Nn12.
Ah, so the theorem is saying that when n is odd, you can actually achieve this theoretical maximum.
Exactly. And the proof usually involves a visual construction. Imagine placing the n vertices in a circle.
Okay, like points on a clock face.
You draw one Hamiltonian circuit, maybe by connecting adjacent vertices around the circle, 1 to 2, 2 to 3, and 1.
Right, the outer polygon.
Then you generate the other circuits by sort of rotating a pattern. You might connect vertex I to vertex I plus 2, modulo n, all the way around. That gives another circuit. Then connect I to I plus 3, modulo n.
Each jump size gives a different circuit.
Exactly. And because n is odd, these different jump patterns, connecting vertices k-steps apart, generate circuits that use completely different sets of edges. You keep doing this until you've generated N12 distinct edge disjoint circuits in total.
That's a clever geometric way to build them. So for K5, N5, you'd expect 512 it equals 2 edge disjoint circuits. For K7, you'd get 712 equals 3.
Precisely. It's a neat result.
And this connects to that seating arrangement problem example.
It does perfectly. What's the setup for that one?
It was 9 club members. They sit at a round table every day. They want to arrange it so that each day everyone has 2 completely new neighbors compared to any previous day.
Okay, 9 people, round table, new neighbors, daily. How do we model this with graphs?
The 9 members are the vertices. Since anyone can potentially sit next to anyone, it's a complete graph, K9.
Right. And a specific seating arrangement around the table.
That's a Hamiltonian circuit. It orders all 9 vertices in a cycle.
Good. And the condition of having different neighbors each day.
That means we need edge-disjoint Hamiltonian circuits. Each circuit represents a valid seating, and the edges represent the neighbor pairs for that day.
Uh-huh. So we need to find the number of edge-disjoint Hamiltonian circuits in K9. We have NN9, which is odd, and N is 3.
So we use Theorem 2-3. The number is 9 to 1, 2.
Which is 4.
So they can manage this for 4 days before they have to repeat neighbor pairs. That's a surprisingly practical application.
It really is. Shows the power of the abstraction. Now, a word of caution. Finding Hamiltonian circuits in general graphs, not necessarily complete, is notoriously hard. It's a famous NP-complete problem.
Right. But there are some conditions that guarantee one exists even if they aren't necessary, like Dirac's theorem.
Exactly. Theorem 2 to 4, Dirac's theorem. It gives a sufficient condition. It says if you have a simple graph with n vertices, where n equals 3, and every single vertex has a degree of at least n2.
So each vertex is connected to at least half the other vertex.
Then the graph is guaranteed to have a Hamiltonian circuit.
Guaranteed. But it's only sufficient, not necessary. Meaning a graph could have a Hamiltonian circuit even if some vertices have degrees less than n2.
That's a crucial distinction. Dirac gives you a yes if the condition is met, but it doesn't give you a no if it's not met. The circuit might still exist.
Okay. And this whole Hamiltonian circuit idea leads directly into the traveling salesman problem, the TSP.
Ah, yes, the TSP. Everyone's heard of it, probably. What's the basic goal?
Salesman needs to visit a set of cities, knows the distance between each pair, wants the shortest possible round trip that visits every city exactly once, and returns to the start.
Okay, how's that a graph problem?
Cities are vertices. The known distances are weights on the edges between them. We usually assume it's a complete graph. Can get between any 2 cities, maybe indirectly, but we have a cost.
Yeah.
We're looking for
A Hamiltonian circuit where the sum of the weights, distances, on the edges of that circuit is minimized.
the minimum weight Hamiltonian circuit, and finding it is hard.
Extremely hard computationally. Theoretically, you could list all possible Hamiltonian circuits. For n cities, that's n 1.2 circuits.
Factorial. That grows incredibly fast.
Astronomical is the word. You could calculate the total distance for each one and pick the smallest. But for even, say, 20 cities, the number of circuits is just too vast for any computer to check in a reasonable time.
So finding the absolute best TSP tour is computationally infeasible for large numbers of cities. People use heuristics and approximation algorithms instead.
Exactly. It's a great example of where the theory, Hamiltonian circuits exist, meets the harsh reality of computational complexity.
Okay, that's a good overview of Hamiltonian stuff. Now let's switch gears again. Directed graphs or digraphs, what's the key difference?
Direction matters. In a digraph, the edges have arrows. Each edge is an ordered pair of vertices, V, Vj, meaning it goes from Vi to Vj.
Initial vertex to terminal vertex. And you can have self-loops, right? An edge from a vertex back to itself.
Yep, self-loops VV are allowed in digraphs.
And with direction, we get new degree concepts. In degree and out degree.
Right. Out degree of V, D plus V, is the number of edges starting at V, going out. In degree dV is the number of edges ending at V, coming in.
And there's a basic property relating these.
Yeah, if you sum up all the in degrees in a digraph, it must equal the sum of all the out degrees, and both sums equal the total number of edges in the digraph, kind of a conservation law.
Okay. What about isolated and pendant vertices in digraphs?
An isolated vertex has 0 in degree and 0 out degree, just sitting there, no connections in or out. A pendant vertex is usually defined as having a total degree, in degree plus out degree, of exactly 1, so just one arrow touching it, either in or out.
Got it. And parallel directed edges.
That's when you have multiple edges going from the same initial vertex to the same terminal vertex, like 2 arrows pointing the same way between the same 2 points.
Okay. And we can always take a digraph and just ignore the arrows to get its corresponding undirected graph.
Yep. Just erase the arrowheads, treat every edge as a 2-way street. Useful for checking some properties like weak connectivity later. And isomorphism is similar to undirected graphs. Two digraphs are isomorphic if they have the same connection structure, respecting direction.
Okay, now just like undirected graphs, there are different types of digraphs. Let's run through those definitions quickly. Simple digraph.
Simple digraph means no self-loops and no parallel edges, the most basic, clean type.
Asymmetric digraph.
Asymmetric means between any two distinct vertices A and B, you can have at most one edge. So if you have AB, you cannot have BA. Self-loops are still okay, though.
Okay, and the opposite is symmetric digraph.
Exactly. Symmetric means if you have an edge, AB, you must also have the edge, BA. For every connection, the reverse connection also exists.
And you can combine these, like simple symmetric, simple asymmetric.
Yeah, simple symmetric.
Yeah.
No loops, no parallel edges, and if AB exists, then BA exists.
Hmm.
Simple asymmetric. No loops, no parallel edges, and if AB exists, then BA does not exist.
Okay, what about complete digraphs? You mentioned two types.
Right. First, complete symmetric digraph. It's simple, and there's exactly one edge from every vertex to every other distinct vertex. So you have both A, B, and BA for all pairs, total of n1 edges, sometimes called a tournament graph.
Okay. Second type.
Complete asymmetric digraph. This one is asymmetric, and between every pair of distinct vertices, there's exactly one edge, either AB or BA, but not both. Total of n1 2 edges, like a round-robin tournament where every game has a winner-loser.
Gotcha. And finally, balanced digraphs.
Balanced means for every vertex, its in degree equals its out degree. Number of arrows coming in matches the number going out everywhere, sometimes called pseudosymmetric or isographs.
The regular balanced digraph.
That's a balanced digraph where all the in degrees are the same value and all the out degrees are the same value, equal to the in degree value. Very uniform flow.
Interesting how much richer the classification gets with direction. Now, the material links digraphs to binary relations. How does that work?
It's a really powerful way to visualize relations. A binary relation R on a set X just tells you whether pairs of elements, LUP XJ, are related, written XIR XJ.
Like less than on numbers, or is a friend of on people.
Exactly. You can represent this with a digraph. The elements of the set X are the vertices. You draw a directed edge from a knee-sup to XJ if and only if XIR XJ is true.
Okay, so the digraph is the relation. Let's look at properties. Reflexive relation.
Reflexive means every element is related to itself. IR for all 11. In the digraph, this means every single vertex must have a self-loop.
And irreflexive means no self-loops.
Correct. Symmetric relation. We talked about symmetric digraphs.
Right. If it can IRXJ, then XJRY. So edge RUIU exists, then edge XJ or love must also exist. The digraph is symmetric.
Perfect. Transitive relation. Transitive. If XRXJ and XJRXK, then it must be that XRXK, like is an ancestor of. The digraph representing this is called a transitive directed graph. If there's a path from is_I to xj and from xj to xk, there must be a direct edge from xi or already a path. It's a bit more complex to see visually sometimes.
Okay, and equivalence relations, those combine properties, right?
Yep. An equivalence relation must be reflexive, symmetric, and transitive, like is equal to or lives in the same city as.
What does the corresponding equivalence graph look like?
It partitions the vertices into disjoint sets, the equivalence classes. Within each set, every vertex is connected to every other vertex. It forms a complete undirected subgraph because of symmetry and transitivity, and every vertex has a self-loop because of reflexivity.
So it looks like a bunch of separate, complete graphs, each with loops on all its vertices.
Exactly that structure.
And relation matrices are just another way to write this down.
Yeah, a matrix A, where Aij is 1 if XIR XJ and 0 otherwise. A001 matrix that captures the whole relation algebraically. Useful for computation.
Okay, let's talk about paths and digraphs. There's a difference between directed paths and semi-paths.
Yes, crucial difference. A directed path from A to B follows the arrows correctly the whole way, like driving on one-way streets.
Okay, a semi-path.
A semi-path from A to B is just a path in the underlying undirected graph. You can traverse edges forward or backward, ignoring the arrows, just to show there's some connection.
So a directed path is always a semi-path, but not necessarily the other way around.
Exactly. And related are directed walks, can revisit vertices but follow arrows, don't repeat edges, and semi-walks, walk in the underlying undirected graph. And similarly for circuits and semi-circuits, closed versions.
Got it. Connectivity in digraphs also seems more layered, strong versus weak.
Right. Strongly connected means you can get from any vertex to any other vertex by following a directed path, following the arrows. Very high level of connection.
Okay. Weakly connected.
Weakly connected means the underlying undirected graph is connected. So if you ignore the arrows, you can get from anywhere to anywhere else, but you might not be able to follow directed paths between all pairs.
And if even the underlying graph isn't connected, then the digraph is just disconnected.
Correct.
And components versus fragments.
Components are the maximal weakly connected subgraphs, the big connected pieces if you ignore arrows. Fragments, or strongly connected components fragments, are the maximal strongly connected subgraphs, pockets within the graph where everything inside can reach everything else inside following the arrows.
So a weakly connected graph might contain several separate strongly connected fragments.
Exactly. And this leads to the idea of the condensation of a digraph.
What's that?
You shrink each strongly connected fragment down to a single supervertex. Then you draw an edge between two supervertices if there is any edge in the original digraph going from the first fragment to the second fragment.
So it shows how the strongly connected pieces are linked.
Yes. And a key property. The condensation graph never has any directed circuits. It's always a directed, acyclic graph, or DAD.
Interesting. Finally, accessibility or reachability.
Simple idea. Vertex B is accessible, or reachable, from vertex A if there's a directed path from A to B. Strong connectivity just means every vertex is accessible from every other vertex.
Okay, that covers a lot on digraphs. Let's circle back to algorithms for a moment. Fleury's algorithm. What's its purpose again?
Fleury's is specifically for finding an Euler path or Euler circuit in an undirected graph, assuming one exists.
Right, back to traversing edges. What are the steps?
Okay, 4 main steps. 1, check the degrees. You need 0 odd vertices for a circuit or exactly 2 odd vertices for a path. If not, stop impossible.
Step 1, check feasibility.
Step 2, choose a starting point. If 0 odd vertices, start anywhere. If 2 odd vertices, must start at one of the odd ones.
Okay, start appropriately.
Step 3, traverse edges. Pick an unused edge connected to your current vertex. Here's the crucial rule. If you have a choice, do not choose an edge that is a bridge in the graph of remaining untraversed edges unless you have absolutely no other choice.
A bridge being an edge whose removal would disconnect the remaining graph. Why avoid bridges?
Because if you cross a bridge too early, you might burn your only way back to the part of the graph you just left, stranding edges over there before you've traversed them.
Don't trap yourself. So prefer non-bridges. If only bridges are left, pick one.
Right. Step 4, keep going until all edges are traversed. You'll naturally end up at the correct place, the start for a circuit, the other odd vertex for a path, if you follow the bridge rule.
Let's trace that example from the material quickly. It had vertices 0, 1, 2, 3. Edges 0, 1, 0, 2, 1, 2, 2, 3.
Okay, first degrees. Vertex 0 degree 2, even. Vertex 1 degree 2, even. Vertex 2 degree 3, odd. Vertex 3 degree 1, odd.
2 on vertices, 2 and 3. So an Euler path exists, must start at 2 or 3. Let's start at 2.
Okay, from vertex 2, edges available, 2, 0, 2, 1, 2, 3. Is any of them a bridge right now?
If I remove 2, 0, the graph 0, 1, 2, 3 is still connected. If I remove 2, 1, still connected. If I remove 2, 3, vertex 3 becomes isolated. So 2, 3 is a bridge.
Right, so Fleury says avoid 2, 3 if possible. Let's take edge 2, 0. Path is now 2, 0. We're at vertex 0.
Okay, at 0, only unused edge is 0, 1. No choice. Take it. Path 2 is 0, 1. We're at vertex 1.
At 1, only unused edge is 1, 2. No choice. Take it. Path 2, 0, 1, 2. We're back at vertex 2.
Okay, back at 2. What unused edges are connected to 2 now? Only 2, 3 is left.
And is 2, 3 still a bridge in the remaining graph, which is just the edge 2, 3? Well, technically yes, but it's our only option.
So we have to take it. Path 2, 0, 1, 2, 3. We're at vertex 3.
Are there any edges left?
No, we use 2, 0, 0, 1, 1, 2, 2, 3. That's all 4 edges.
And did we start at an odd vertex 2 and end at the other odd vertex 3?
Yes, we did. So 2, 0, 1, 2, 3 is the Euler path found by Fleury's algorithm.
Perfect trace. The bridge avoidance rule is key.
It really guides you through it. Okay, wow, we've covered a ton of ground.
We really have. Eulerian graphs, Hamiltonian graphs, theorems, operations, digraphs, types, relations, connectivity, Fleury's. It's a solid chunk of graph theory.
Absolutely. Hopefully this deep dive gives everyone listening a much stronger handle on these fundamental concepts, almost like, as you said, prepping for a test on it. It provides a framework for thinking about networks and relationships.
Definitely. Understanding these structures, how paths are constrained by vertex degrees, or the need to visit every vertex is crucial for tackling problems in logistics, networking, social analysis, even biology.
So maybe a final thought for our listeners to chew on. Beyond the obvious math and CS applications, where else might these ideas of Euler and Hamiltonian paths pop up? Think about, say, supply chains, maybe neuroscience, or even planning a road trip.
Could the efficient routing of a garbage truck be an attempt at an Euler circuit? Could mapping protein folding involve Hamiltonian path concepts?
Exactly. Keep an eye out for these patterns in unexpected places. You might be surprised how often these graph theory concepts are lurking beneath the surface. Thanks for joining us on this deep dive.